Hello and welcome to another NGen Math 8 lesson by eMathInstruction. My name is Kirk Weiler and today we're going to be doing Unit 1, Lesson 8 on modeling with linear equations. So throughout this unit we have been working on solving equations. Sometimes they had variables only on one side, sometimes they had variables on both sides. Most of these equations that we've solved, it's just been, here's the equation, solve it. Right? But there are lots and lots of real-world scenarios that can be modeled, meaning that they can be mathematically described using these types of equations. Then, of course, solving them gives us some kind of piece of information that is helpful to us in some way. All right? So today what we're going to be doing is we're going to be modeling different scenarios that you can handle using these types of equations. All right? And then, of course, solving those equations to find something that we need. All right, let's get into our first problem right away. All right, here we go. Exercise number 1. A rectangle has a length of 25 feet and a width given by the variable w. Letter A asks us, what is the perimeter of the rectangle when w equals 10 feet? Show the calculation you use to find your answer. Now, you've been doing perimeter for a long time. So what I'd like you to do is I'd like you to pause the video now and figure out what the perimeter of this rectangle would be given that its width is 10 feet. All right, let's go through it. So, as you well know, right, the perimeter is just the sum of the lengths that go all the way around the rectangle or whatever figure you're dealing with. Now, it's important, obviously, to distinguish that from area, right? And we're going to do an area problem in just a bit. But if w is equal to 10, right, then of course I've got a 25 and a 25 and a 10 and a 10. It's most easy to find the perimeter then to use something like this. Oh, well, I've got 2 times 10 plus 2 times 25, right? And of course 2 times 10 would be 20, 2 times 25 would be 50, and I would just have 70 feet. All right, nothing very difficult about something like that. But it's always important to make sure that you understand what you're doing when you know all the numbers, so that when you move to a situation where you've got a variable involved, you know what you're doing there as well. Given that, let's take a look at letter B a little bit together. I want to keep the picture on the board, but letter B says, write an algebraic expression in terms of w for the perimeter of the rectangle. Now, this is very important, right? Language in mathematics is important. Write an algebraic expression, not an equation. I want an expression in terms of w, meaning that there's going to be a w in it, for the perimeter of this rectangle. Well, the perimeter of the rectangle is going to be w plus 25 plus 25, right? So I could start by just saying, well, it's going to be w plus 25 plus 25, and that actually would be a perfectly good expression for the perimeter, but it kind of makes sense to combine like terms and say that the perimeter will be given by 2w plus 50. And keep in mind, this is exactly what we did up here, right? When we knew that w was equal to 10, we took that 10, we multiplied it by 2, we got 20, and we added the 20 to the 50. It's a little bit missing here, but we can scroll up there, right? That is 2w plus 50 when w was equal to 10. Here, we've got an expression so that I could give you now any value of w. You could put it into this expression and calculate the perimeter. But now, let's take a look at where an equation might come in, letter C. Using your expression from B, set up and solve an equation that finds the value of w for a perimeter of 64 feet. All right, well, this is an expression that gives us the value of the perimeter if we know the value of w. But now we know the value of the perimeter and we want the value of w. So what do? Well, we simply say, here's my perimeter, 2w plus 50, and I set that equal to 64, right? That literally models the scenario going on in C. Here's the perimeter in terms of w, and we know it's equal to 64 feet. Now what I'd like you to do is pause the video just for a few minutes and solve this and find the width. All right, let's go through it. So it's simple enough. We're already ready to solve this simple two-step equation. I'm just going to subtract a 50 from both sides. That's going to give me 2w is equal to 64 minus 50, which is 14, right? I can now divide both sides by 2. And of course, 14 divided by 2 gives me a width of 7 feet. Now, just for a moment, I want you to think about how the solution of this equation corresponds to what you could have probably done years ago in solving this problem, right? Years ago, if I had given you a picture like this and I had said, hey, the perimeter of this rectangle is 64 feet, figure out the width, you very well may have said, well, let's see, I've got 64 feet and I know 50 feet are taken up by those two sides, so let me just subtract those two, right? That leaves me with 14 feet. Right? And then I've got to divide that 14 feet up amongst the two sides that represent widths. So I have 14 divided by 2, and I get 7. So really, the steps that we use in solving this equation are very, very similar to what we would have done had we not had algebra in the first place. Okay? Now, let's go on, though, and see some other types of problems that also involve modeling using linear equations. All right, more modeling based on geometry. We just did some perimeter. Let's bring area into it. Exercise 2. In the diagram below, all lengths are given in feet, including the unknown length of x. The two rectangles have equal areas. Letter A asks us to determine the value of x algebraically. Whew. All right, so I'm telling you, these two rectangles have equal areas, right? And I want to somehow model the fact that they have equal areas given what they've shown me and somehow use it to figure out the value of x. Well, keep in mind that the area of any rectangle is sort of length times width or base times height or however you want to put it. It's this dimension times this dimension. So the area of this particular rectangle is 5 times x. I'm going to actually just write that into the rectangle. Okay? And the area of this rectangle, a little bit trickier, is going to be 2 times x plus 6. I think I'm just going to write that like this for right now. All right, those parentheses are really critical. Very, very different if you've got 2x plus 6 without the parentheses. Now, how do we model the scenario? Well, we are told that the areas of the two rectangles are equal. So I'm simply going to take this area, which is 5x, and I'm going to set it equal to that area, which is 2 times x plus 6. That models this scenario. And now what I'd like you to do is pause the video and solve this equation. All right, let's go through it. Not a lot that we have to do. We're going to use the distributive property to simplify the right-hand side of that equation. So when we distribute the 2 through the parentheses, we'll get 2x plus 12. All right, I'm going to subtract a 2x from both sides of the equation. All right, 5x minus 2x is 3x. I get 3x equals 12. Divide both sides by 3. And 12 divided by 3 gives me 4. 4 feet. Now, we've got a fantastic check in this problem, right? And the check is basically this. The two rectangles are supposed to have the same area. So in letter B, it says, what is the common area of the two rectangles? Well, this is really kind of cool because, again, right, we know that x is equal to 4, or at least we think it is. In which case, that rectangle has a length of 4 and a length of 5 and a width of 4. This one has a width of 2, and if I put 4 in here, right, I then get a width of 10. So if I've done this correctly, the two areas should be the same. Well, the rectangle on the top has dimensions of 5 by 4, so that's going to be 20 square feet. And the one on the bottom has dimensions of 2 times 10, and that's also going to be 20 square feet, right? And that's a beautiful check in terms of whether or not we've done the modeling correct and whether or not we've done the algebra correct. They both have the same area. All right, lots and lots of geometric problems can be modeled with the algebra that we know at this point. We're going to see it throughout the course, especially given that units 2, 3, and 4 of Math 8 are really geometry heavy. So we'll see a lot of this type of work. Let's keep going. All right. One of the things that you see a lot in algebraic modeling, for what it's worth, are problems based on people's ages. So let's take a look at exercise 3 on a problem like that. Shayna's age is 8 years more than 3 times Evie's age. Wow. Shayna's age is 8 years more than 3 times Evie's age. Always read it as many times as you need to. Let the variable E represent Evie's age. Letter A says, if Evie was 7 years old, how old would Shayna be given the information in the problem? All right, I want you to pause the video right now because I can't oversell how important letter A is. If you can't do letter A, it's pretty much impossible to do B, C, and D. So take a moment and try to figure out if Evie was 7, how old Shayna would be. All right. Well, specifically, the problem tells us that Shayna's age is 8 years more than 3 times Evie's age. So if Evie is 7 years old, right, then we could do 3 times 7 and get 21, right? That's 3 times Evie's age. And then we'd do 21 plus 8, and we'd get 29, right? So Shayna would be 29 years old, which we're getting by just doing 3 times Evie's age plus 8. Letter B says give an expression for Shayna's age in terms of Evie's age, E. So again, when you do something like B, what you want to do is exactly what you did in A, except instead of having 7 in here, you want to have the letter E. Pause the video for a moment and see if you can write down an expression for Shayna's age based on Evie's age. All right, so let's go through it, right? We want an expression for Shayna's age in terms of E, and what we really want to do is we want to do exactly what we did in letter A, which was why that one was so important. Now, what did we do? In letter A, we took Evie's age, right, 7, we multiplied it by 3, and we added 8. So that's exactly what we want in B, right? Which is that we want to take Evie's age, we want to multiply it by 3, and then we want to add 8 to that result. 3E plus 8, then, is an expression that given Evie's age, any age for her, right, we can plug it into that expression and we'll get Shayna's age. Now let's get into the equation solving in letter C. If the sum of their ages is 56 years, set up and solve an equation to find the value of E. Now we have to be careful here because the tendency would be to take 3E plus 8 and set it equal to 56 and solve. But that doesn't properly model the scenario, right? It says the sum of their ages is 56 years, set up and solve an equation to find E. So let's do that together, right? I mean, if we're going to sum their ages, we start with Evie's age, E, and we add to it Shayna's age, which is 3E plus 8. That then is going to be equal to 56, right? This equation models the scenario because it's the sum of Evie's age plus Shayna's age is equal to 56. What I'd like you to do now is pause the video, solve this equation to find Evie's age, and then also in letter D, figure out how old Shayna is. All right, this isn't too bad. What we're going to do is on the left-hand side here, we have to do a little combination of terms, but then it's going to be simple. Let's do this together. Here we go, right? E plus 3E is equal to 4E, plus 8 is equal to 56. We're going to subtract an 8 from both sides, right? That's going to leave us with 4E is equal to 56 minus 8, which is 48. Divide both sides by 4, and E ends up being 12. So Evie is 12 years old. Now, letter D asks us how old Shayna is. Well, conveniently enough, we have an expression right here, 3 times E plus 8, which will tell us then how old Shayna is. So let's do that. We have 3 times 12 plus 8. 3 times 12 is 36 plus 8. And 36 plus 8 is 44. Evie is 12 and Shayna is 44. All right, that's it. Again, we use information in the problem to do some modeling, and then we use our equation solving techniques to figure out what we're looking for. Let's keep going and do a little more modeling with algebra. Equation number 5. Equation number 5. Exercise number 4. I'm all over the place. Levi is currently 41 years old and his daughter Nora is 5. In an unknown number of years, n, Levi will be 4 times as old as Nora. All right, letter A asks us, how old will they both be in 13 years? How many times older is Levi than Nora at this point? Okay, so, it's important, again, just to be able to sift through the information they give you. So what I'd like you to do is try to figure out the answers, both this one and this one, to letter A. All right, well, figuring out how old both of them are in 13 years, that's not too hard, right? So Levi is going to be 41 plus 13. So Levi is going to be 54 years old in 13 years. And then Nora is going to be 5 plus 13, which is equal to 18 years old. If we want to know how many times older Levi is than Nora, right, then that means I'm going to do 54 divided by 18, or if you will in fraction form, 54 divided by 18, right? And that's going to be 3, right? So literally, if I do 18 times 3, right, I get 54. So after 13 years, Levi is 3 times as old as Nora is at that point. But in our problem, it says Levi is currently 41 years old and his daughter Nora is 5. In an unknown number of years, n, Levi will be 4 times as old as Nora. So after 13 years, Levi is 3 times as old as Nora. The question is, for letter B, we want to set up and solve an equation to find the value of n. We want to set up and solve an equation that will allow us to figure out how many years it's going to take before Levi is 4 times as old as Nora. Then I want to check to make sure that Levi is, in fact, 4 times as old as Nora at this point. All right, so let's take a look at this, right? This unknown value of n. Well, what's the modeling we have here? Well, we know that Levi in n years will be 41 plus n years old, right? So that's Levi's age. On the other hand, Nora is going to be 5 plus n. That's going to be Nora's age. Now, what we're told in the problem is that Levi will be 4 times as old as Nora. So how can we use that to model? Well, here's Levi's age, 41 plus n, and that's going to be 4 times Nora's age, 5 plus n. And just do this, just so that we can really see that. Let's talk about this a little bit. This is really kind of cool, right? Levi's age is 4 times Nora's age. And boy, are those parentheses again important. Without those parentheses, it would look very strange, number one, and it would also mean that we wouldn't be multiplying all of Nora's age by the number 4. Now, solving this equation shouldn't be too tough. So I'd like you to pause the video right now and try to figure out the value of n. All right, let's go through it. Now, there's not much I need to do on the left-hand side, but I may want to use the commutative property of addition to rewrite that as n plus 14 instead of 14 plus n. On the other hand, on the right-hand side, we're going to use the distributive property, 4 times 5 is 20, and 4 times n is 4n. Now again, it may make sense to do a couple things at this point. One thing we might want to do is use that commutative property again to rewrite the right-hand side as 4n plus 20. And then I think I'm going to even use the trick where I flip the equality so that I'm sitting at 4n plus 20 equals n plus 14. It's just going to make my solving easier. I can now subtract an n from both sides. That's going to give me 3n. Whoops, sorry about that. 3n plus 20 is equal to 14. Oh, I see what I did. I didn't just flip the 41 up here. I flipped 41 and made it 14. That's just strange. Let me just correct that really quick. I'm like, this is not working out whatsoever. I was getting a negative answer, which would have been very, very strange. We would have had to go backwards in time. Oh, that's much, much better. Okay, for some strange reason, when I flipped 41 plus n, I made it into n plus 14. You should definitely not flip-flop the 4 and the 1. Anyhow, now let's finish this off by subtracting a 20 in both cases. All right, we gotta use some room up here now. I have 3n is equal to 21. Divide both sides by 3, and we'll get n equals 7. Sorry about that mistake. Now, one thing that was nice about making the mistake is as I was working it down, I realized I was going to get a negative answer, which immediately told me there was something that was either not realistic about the problem or I had made a mistake, and then I saw it pretty quickly when I rewrite this as n plus 14. Anyhow, one last thing I want to check though is to make sure that in 7 years, right, that in fact Levi is 4 times as old as Nora, right? And that's an easy check to do because I can now take that n equals 7 and maybe I'll do the check over here, right? I can say, well, I mean, in 7 years, right, Levi is going to be 48. On the other hand, in 7 years, Nora is going to be equal to 12. And, right, 12 times 4 is in fact 48. So we know we're right. All right, excellent. Again, sorry about the little mistake there. That could have been quite confusing. Let's keep moving on, do a little bit more modeling. One more problem. Exercise number 5. Laura and Kirk are comparing how much they've been running. Laura has already run 36 miles, and Kirk has run 64. Laura begins running 21 miles per week, and Kirk runs 17 miles per week. How many additional weeks, W, will it take for their total distance run to be equal? All right, so let's do this modeling together, right? We've got this number of weeks W, right? And I want you to think about this for a moment. Let's say, just for a second, right? Let's say W was equal to 2, right? Let's think when W is equal to 2, right? How many miles in total both Laura and Kirk have run? Well, we know, right, that Laura has already run 36 miles and Kirk has run 64. But now Laura is running 21 miles a week and Kirk is running 17 miles. So for after 2 weeks, right, to figure out how far Laura had run, you know, we would probably take that 21 miles per week, we'd multiply it by 2 and we'd get 42. And then we'd take 42 and we'd add it to whatever she had originally run, which was 36. And we'd get 78. So this is just after 2 weeks. On the other hand, after 2 weeks, Kirk, right, he would have run 17 miles a week times 2, which would be 34. And then we would take that 34 and add it to however many he had started at, which was 64, and we'd get 98 miles, right? So this is just if we were kind of saying, all right, well, after 2 weeks of running, you know, how would they compare? Well, Laura would have run 78 miles, Kirk would have run 98. The important thing is, though, what we did is we took the number of weeks times 21 for Laura and then added it to 36. Then we did the number of weeks, 2 times 17, and added that to 64 for Kirk. That's if W is equal to 2. But we're actually looking for W. So the question is, what equation can we set up, you know, to model this problem that will then, when we solve it, tell us how many weeks it will take for their total distances to be the same. Pause the video now and see if you can model this problem just using W. All right, let's do it. Again, we want to do something very similar here, except wherever there was a 2, we just want a W. So for Laura, right, she's going to have 21 times W, right, plus the 36 miles that she started with. That's going to be Laura's distance. On the other hand, Kirk, well, he's going to have 17 times W, right, plus the 64 miles that he began at, right? This is exactly what we've done up here when we know that W is 2, except we've left the W unknown down here. But solving this equation should be pretty simple. Pause the video now and go ahead and do so. All right, let's get into it. Just solving an equation with variables on both sides. We're going to start by subtracting a 17W from both sides. On the left-hand side, we're going to be left with 4W plus 36. On the right-hand side, we're going to be left with 64. Now, of course, we can subtract a 36 from both sides. All right, 64 minus 36, maybe do a little bit of this, is going to be 28. And that's equal to 4W. We now have 4W is equal to 28 divided by 4 on both sides. And it looks like it's going to take 7 weeks before the distance that they've run is the same. All right. Very good example of where we can model a scenario where we end up having a variable on both sides of the equation. And really this comes down to a rate problem again, right? We have a rate, miles per week, another rate, miles per week, and then we have some initial amount, 36 miles and 64 miles, right? By setting up these two sort of rate equations and setting them equal, we can then find out how many weeks it'll take for Laura to catch up to the same amount of distance that Kirk was starting at. All right, let's wrap this lesson up. All right, today we didn't learn anything new in terms of how to solve equations, right? We're actually kind of done with that in a certain sense in Math 8. We've learned all the equation solving techniques we're really going to at this point, with maybe a little exceptions where we specialize later on. But what we did see today was how to model particular types of scenarios using algebra and then solving those equations in order to find some piece of information we wanted. All right, we'll get more practice on this in the next lesson, although it's going to get a little bit more messy, so we'll bring our calculators in then. Thank you for joining me for another NGen Math 8 lesson by eMathInstruction. My name is Kirk Weiler, and until next time, keep thinking and keep solving problems.